Chapter 9 and 10 are both about hypothesis testing. That's why I've grouped them together for this week. I know it seems like a lot for 1 week, but a lot of the background information that I'll talk about at the beginning of Chapter 9 also applies to Chapter 10. So basically, both chapters are about testing hypotheses. So I might have a hypothesis that defects have gone up, or graduation rate has gone down, or crime rate has gone up, or crime rate has gone down. So hypothesis testing is a way to actually test that. So for example, more than 90% of our clients will be satisfied with our customer service. That's what I am hypothesizing. And it's a belief about a population parameter. Basically, either population mean, population proportion, and actually mean and proportion are the only things that we'll cover in this class. And the hypotheses are typically stated before the data are gathered. You don't want the data to inform your hypotheses. You're basing a hypothesis on something you have before you take a sample. Okay, so for example, for the hypothesis testing process, the average work efficiency of employees is at least 90%. That's your hypothesis that you want to test. So you have a population of employees, you take a sample from that population, and let's say from that sample, the proportion is 46%. Well, most likely 46 is nothing like 90%, so statistically you're going to reject the hypothesis. 46 is not statistically significantly close to 90%. Okay, so that's an example of hypothesis testing and some of the steps we'll go through, but we'll go through each step in turn. Okay, so just some background that also applies to Chapter 10. Your null hypothesis, or H naught, with that sub-zero there, is going to be basically the status quo. Like, what are you trying to disprove? It's generally something that's given to be true until we prove otherwise, like innocent. When you have a trial, you assume someone's innocent until you can prove guilt. So basically the null is what you're trying to disprove with the alternate hypothesis. We can think of the alternate hypothesis is proving guilt, or H1, and that's what we're trying to prove. Sometimes called the action alternative because it generally leads to some action. Like, let's say I do find that number of defects have gone up. Well, then I need to check the process, the machines, see what's going on. So in a trial, a jury must decide between two hypotheses. Either the null hypothesis, or H naught, the defendant is innocent. We assume that to be true until we prove otherwise. The alternate hypothesis is the guilt. So basically that's the thing we have to prove. So hypothesis testing is never about trying to prove the null hypothesis. It's all about trying to find evidence or not for the alternate hypothesis. Okay, so one or the other must be true. I typically write out my hypotheses, and then when I find the final conclusion, I cross off the one that I am not going with, because one or the other must be true. They're basically complements to each other, either or. Okay, so let's think about that for a sec. So I make a decision that says the person's innocent. If they are innocent, that's a correct hypothesis. That's a correct conclusion. I don't have to worry about that. But let's say my decision is that they're guilty when they're innocent. That's what's called a type 1 error. And the reason I bring that up is because we're going to talk about level of significance in these two chapters. And level of significance, or alpha, is the probability of that type 1 error. If you recall from chapter 8 when we talked about confidence intervals, we basically chose a confidence level, like say 95%. What the 5% is, 100% minus the 95% confidence, is the level of significance, the probability of a type 1 error. So you can almost call it like the lack of confidence. If I choose a confidence level of 95%, my lack of confidence, or probability of type 1 error, is the 5%. So we'll see level of significance in hypothesis testing. We won't see type 2, but I'm just going to mention it here. You won't see it on a quiz or homework either, but basically that would be if I decided they were innocent when they were actually guilty. But the probability of type 1 error, or alpha, is what we're going to use to make our final conclusions in hypothesis testing. Okay, so like I said, type 1 error, rejecting a true hypothesis. Greek letter alpha represents that, or level of significance is often called, and that's the probability of a type 1 error when a jury convicts an innocent person, for example. Type 2 error, again, you don't need to know this for the quiz, but you don't reject a false null. That's represented with the Greek letter beta, and it's a probability of a type 2 error. So, for example, when a guilty defendant is acquitted. And the two probabilities are inversely related. Decreasing one increases the other. So basically when I'm choosing confidence, I'm also choosing my lack of confidence, or alpha, which is called level of significance. Okay, so an overview of this chapter, we'll do hypothesis testing for a mean, and we'll also do it for proportion. So we saw that in the past with confidence intervals and sample sizes. There was problems that were focused on averages, and there was problems that were focused on percentages. Okay, but for both types of problems, there's a few steps, and these steps apply to chapter 10 as well. Set up the hypotheses. Okay, so there's a few things that go into setting up the hypotheses. We'll figure out whether it's a two-tailed, left-tailed, or right-tailed problem, and I'll explain that in a bit. And are we talking about a mean problem or a proportion problem? We'll pinpoint ways to figure that out when we read the problems. And what is this hypothesized value that we're trying to disprove? So there'll be a number in either an average or a proportion in both of our hypotheses, and that's the value that we're trying to disprove. Okay, then we're going to enter the data in Megastat, and then the final result is to look at the p-value to make a final decision. So, and I'll explain p-value in a minute, but basically if the p-value is less than our alpha, remember alpha is level of significance or probability of a type 1 error. So if a problem says 95% confidence, your alpha is 5%, then you reject the null. That's an important rule right there, because that's going to apply to all problems in chapter 9 and all problems in chapter 10. If the p-value, which I'll explain what p-value is in a minute, is less than alpha, reject the null and support the alternate. So basically, if we were talking about innocent versus guilty, if the p-value in my output from Megastat is less than the alpha, then I would reject the null of innocent and prove guilty. Okay, so step 1 is all about setting up the hypotheses. Let's say a student claims that MBA students prepare more than 5 cases per week. Notice the more than. So that's what's being claimed. So what's being claimed is always in the alternate hypothesis. The thing we're trying to prove different from 5, and in this case we're trying to prove more than 5. So notice I've got the H0, the null, and the H1, which is my alternate. I typically write out the alternate hypothesis first, because typically that's going to be, that's the claim. That's what's highlighted in the problem. This more than 5 is the claim, so that's going to go in the alternate hypothesis. And notice it's not a proportion problem. I'm not talking about like 5% of their work is on cases or something like that. So because of the more than, the greater than sign is in the alternate hypothesis. And since it is an average or a mean problem, I'm using mu for my symbol, because hypothesis testing is always about testing hypotheses about your population. You're hypothesizing about the population. So mu will be in both hypotheses. The 5 will be in both hypotheses. Remember, these are complete complements. Either one or the other is what you're going to go with. So there's always the same number in both hypotheses. Either I prove more than 5 cases or I don't. So basically, I'll put the claim first, mu greater than 5. The complete complement or opposite of that is the less than or equal to 5. Now just a quick rule here, if you just always put the equal sign in the null, you'll be correct. Because if I just change this from less than or equal to just equal to, you'll end up with the same result. You're just trying to prove the greater than 5, which is in the alternate hypothesis. Here's an example of a left-tailed hypothesis or a less than problem. Tom's car gives gas mileage of 20 miles per gallon. Will installing new tires lower the mileage? So we're wanting to test this new information. We think it'll be less than 20. Okay, so I'm going to put my claim first. My alternate hypothesis, or H1, is that mu is less than 20. And then it's easy to write the null because it's the complete complement. that mu is greater than or equal to 20. And again, I could put just equal to there. I'll get the same result. But notice also I'm using population symbols. Mu is the population symbol for mean. I've got 20 in both of the hypotheses, because that's what I'm trying to prove or disprove, that it's lower than 20 or equal to 20 or above 20. And then a new cola bottling machine is installed. Is the mean volume different from 12 ounces? So here's an example where I'm not trying to say it's more, I'm not trying to say it's less. So my claim is that it's different from, which is the same as not equal to. Okay, if it just says something like that, different from, then you want the not equal to sign in your alternate hypothesis. Notice I still have the population symbols. It's a mean problem. It says mean volume. And 12 is in both hypotheses. So the null always has the equal sign. You see for all three examples, the null has the equal sign. And the three possibilities for the alternate hypothesis, greater than, like more than 5 cases, less than, like lower the mileage, and not equal to, like is it different from 12 ounces. So that's setting up the hypotheses. Let's look at a quick example. Let's say a fast food chain currently brings in profits of $20,000 per store per day. So notice that's kind of information from the past. We're assuming that's true until we prove otherwise with some new information. A new menu is proposed. Would the new menu be more profitable? So basically what I'm trying to prove is that profits have gone up with the new menu. So what we're trying to claim, what we're trying to prove and find evidence for is that the profits are greater than 20,000. So the complement to that, or the null hypothesis, is we don't find that. We find that it's 20,000 equal to 20,000 or less than 20,000. Okay, so the next step is to actually get the data so that we can enter it. And we always begin with the assumption that the null is true. Like I mentioned, always assume innocent until proven guilty. So until we have further statistical evidence, we assume that the profits are 20,000 or less. The goal of the process is to determine whether there is enough evidence to infer that it's actually gone up with the new menu. So we're going to take a new sample of stores that have these new menus, and hopefully their profits are greater than 20,000 so that we can prove that the menu works. If the new menu works, then profits should be greater than the past, the status quo, the benchmark that we're trying to disprove. Okay, so we have two possible decisions. Conclude that there is enough evidence to support the alternate hypothesis. In that case, we reject the null. Or conclude that there is not enough evidence that it's greater than 20,000, so not enough evidence to support the alternate hypothesis, so we do not reject the null. So basically, we're either rejecting or not rejecting the null. If we find evidence for the alternate, we're rejecting it. If we don't find evidence for the alternate, we're not rejecting it. We have to go with the innocent if we didn't prove guilt. Okay, the next step would be to enter the data. So then I need to get some data to enter. So 36 stores are randomly selected. All those stores have the new menu, so we're wanting to know the average profits of those stores. The average of their daily profits ends up being 21,000 with a standard deviation of 2,400. Notice I can't just stop there. I can't just say, oh, well, 21,000 is greater than 20,000, so yes, the new menu works. We have to test whether it's statistically significantly different or not. We have to prove that 21,000 is statistically significantly greater than 20,000 in profits. And what goes into that is, the standard deviation is actually pretty high. It's almost like saying 21,000 in profits, give or take 2,400. Well, if you subtract 2,400 from it, you're below the 20,000 from the past. Okay, so step 2 is to enter the data. You'll notice under Megastat, if you go to add-ins, Megastat, hypothesis tests, we'll go to mean versus hypothesized value. So basically this is a mean problem, not a proportion problem. You see, we'll be doing mean problems versus hypothesized value and proportion versus hypothesized value in chapter 9. And then comparing two independent groups, paired observations and comparing proportions is chapter 10. Okay, one thing to note here for Megastat, you either have the option of entering the actual data. So if I had all the profits from those 36 stores, so basically a column of 36 values, then I would enter the data. In this case, notice I only have the mean and the standard deviation and the sample size. So that's why I clicked on summary input. And you see there underneath that bar, it says select the range with the label, mean, standard deviation, and sample size. So basically what that means is Megastat is looking for a list that has a label, and then the next row is the mean, and then the next row is standard deviation, and the next row is sample size. Okay, and once I have the data, I put in the hypothesized mean, in this case 20,000 in profits. I'm saying that it's gone up, so my alternative hypothesis is greater than the 20,000. Always going to use t-tests here. It's the more conservative approach when we don't have the population standard deviation, and it's rare to have the population standard deviation, so we'll just use t-test here. And confidence interval. So if it says level of significance of 5, you would choose 95% confidence. Here's what's going into it. I just wanted to show you this, even though Megastat will do this for you. Notice how you're comparing the sample mean to the 20,000, that mu. You know, your estimate of mu is 20,000, so you're going to do 21,000 minus 20,000. And notice that the standard deviation and sample size have to be a part of it. If, you know, I had a really low sample size and, you know, tons of variability, then it's less likely that that 21,000 is going to be proven to be greater than 20,000 statistically, significantly. Okay, so I put in the label, new menu, the average of 21,000, the standard deviation of 2,400, and the sample size of 36. Go ahead and select that for your input range. The hypothesized mean of 20,000, it's a greater than problem, and I can leave those other two. And here's what you end up as a result. Remember I talked about p-value. So we'll talk about what that means now. So the end result is a p-value, which is the probability of getting what you got or something greater if the null is true. So since that p-value is so small, the null must not be true. Okay, I'll explain that again. Okay, so if the p-value is less than alpha, reject the null. Okay, so since the 0.0086 was the p-value, that's less than my alpha, or level of significance, of 0.05. Okay, and we reject the null. So we do have evidence that the new menu works because we found evidence that that 21,000 is statistically significantly greater than the 20,000. And whenever we reject the null, we're basically saying we have enough evidence to accept the alternate hypothesis. Okay, so here again is what the p-value is. It's the probability of getting the result that I got, so that 21,000 from the 36 stores, or something greater, since this was a greater than problem, is 0.0086 if the null is true. So the reason why I'm rejecting the null is there was such a low probability of that occurring if the null is true, so the null must not be true. Okay, so therefore, since it's so unlikely, I have evidence against the null. So I won't on a quiz ask you, what does the p-value represent? I'm more concerned with you get the end result. P-value is less than alpha, so what does that mean? That means the profits went up. That means we should use the new menu. We should implement the new menu in more stores. Okay, I'm more concerned about that. Okay, so in other words, since the p-value is less than alpha, reject the null and support the claim that the profits went up. Okay, and if you've written out the hypotheses, it's kind of nice at this point to just cross off what you know is not right. You found evidence for the 20,000, and you also know you can reject the null. So I often just cross off the null the second I know I can reject it. So either you're crossing off the null or circling the null. Either you found evidence for the alternate, so you reject the null, or not. Okay, and just again about the p-value, some different wording here. A p-value is the probability of the sample result, or one more extreme. So this is describing the p-value not in the context of the problem we just saw, assuming that null is true. Okay, so if it was a less than problem, it would be a p-value is the probability of the sample result, or 1 less, assuming the null is true. So small p-values lead us to believe that the null hypothesis is not true. And the conclusion is that the alternate is true. Okay, let's look at some questions. What if I had this on a quiz? The owner of a local nightclub has recently surveyed a random sample of 300 customers. She'd like to determine whether or not the mean age of the customers is over 35. Notice the over 35. That's what she's trying to prove. If so, she plans to alter the entertainment to appeal to an older crowd. If not, no entertainment changes will be made. So if you want to pause it and just take a look at these for a sec to get the right answer, you can do so. But like I said, she's trying to prove the over 35. So we definitely want a greater than 35 in the alternate hypothesis. Remember, the alternate hypothesis is always what you're trying to prove. I can eliminate C and D because that shows X bar instead of mu. And I always want the population symbol in the hypotheses. So now I'm down to A and B. Well, the greater than sign has to be in the alternate hypothesis because she's trying to prove that it's over 35. So B would be the correct answer. Okay, and which kind of problem is this? To answer that, we always look at the alternate hypothesis. So we picked B, and it's a greater than problem. So that would be a right-tailed problem or a greater than problem. Since you're using Megastat, you don't need to worry too much about right-tailed, left-tailed, two-tail. Just know whether it's a greater than problem, a less than problem, or a not equal to problem. And that's always going to be the symbol that's in your alternate hypothesis, the thing that you're trying to claim. So for the new menu example, it would be greater than, or a right-tailed problem, because we wanted to prove that the profits went up. In this case, she wants to prove age is over 35. Okay, well, let's say you had this problem on a quiz. A spouse stated that the average amount of money spent on Christmas gifts for immediate family members is above $1,200. Notice it says average, so you do know this is a mean problem, not a proportion problem. Also, we haven't done proportion problems yet, but that's one way to note that. And he's saying, or he or she is saying above 1,200, so the 1,200 would be, or greater than 1,200 would be in your alternate hypothesis. So C is the only one that has greater than 1,200 in the alternate hypothesis. Notice B and D could not be correct because the null has to have the equals symbol. Okay, so I don't have to say in the null that it's less than or equal to 1,200. I'll get the same result if I just use the quick rule of just putting the equal sign in the null. Okay, so C is correct there. Above 1,200, so my claim or alternate hypothesis has the greater than sign. Okay, so that would be another right-tailed test or greater than problem.